Is Jupiter a failed star? This question may seem like something out of a science fiction novel, but it's a puzzle that has intrigued astronomers and science enthusiasts alike for generations. Picture this colossal gas giant, the largest planet in our solar system, potentially hiding the secrets of a star that never got its chance to shine. What if Jupiter wasn't just the king of planets, but also a celestial body that had almost made it to stardom? This idea sparks a whirlwind of excitement, not just for the mystery it entails, but for the way it challenges our understanding of what makes a star. Jupiter's massive size and striking composition make it a fascinating subject of study, and its story might just reshape our perception of the solar system we call home. So join us as we explore the enigma of Jupiter and its starry aspirations, unraveling the truths that lie beyond its swirling clouds. Whether you're a space aficionado or just curious about the universe's secrets, you're in for an enlightening journey through the wonders of our cosmic neighborhood. Understanding Jupiter, the gas giant, we begin by delving into its mesmerizing attributes. Jupiter is not just the largest planet in our solar system, but it's a true titan among celestial bodies. Imagine it as a behemoth more than 300 times the mass of Earth, yet composed mainly of gas. Its vastness is mind-boggling, spanning more than 11 times the diameter of our planet. Picture this massive sphere made primarily of hydrogen and helium, much like a star. This ocean of gases swirls with colors and storms, notably the Great Red Spot, a storm larger than Earth that has likely raged for centuries. Jupiter's thick atmosphere, composed of these elements, contrasts with Earth's rocky terrain, offering a glimpse into the universe's diverse planetary designs. The planet's gravitational pull is so strong that it greatly influences the asteroids and comets passing through our solar system, acting somewhat like a cosmic shield for its neighboring planets. Its unique magnetosphere, the largest structure in the solar system, stretches millions of miles and interacts with solar winds in fascinating ways. These features highlight Jupiter's distinctiveness and importance in our solar neighborhood, making it a captivating object of study and speculation. Whether through its immense scale or its dynamic atmosphere, Jupiter serves as a reminder of the awe-inspiring complexity and grandeur of our universe. The concept of a failed star might sound dramatic, but it's actually a term astronomers use to describe celestial bodies that almost had the potential to ignite like a star. Imagine the universe as a colossal talent show, where celestial bodies audition to become stars by showcasing one crucial talent: the ability to sustain nuclear fusion in their cores. This nuclear fusion is the process where hydrogen atoms combine to form helium, releasing immense energy in the form of light and heat. Now, for a celestial body to transition from planet to star, it needs to gather enough mass to reach extremely high temperatures and pressures at its core. This is what sets the stage for nuclear fusion. However, not every aspiring star gets to shine. Some, like Jupiter, fall short in this cosmic contest. They amass a significant amount of gas and material, but not quite enough to ignite fusion. These are the so-called failed stars. Unlike stars, they lack the gravitational squeeze necessary to kickstart the fusion process. Without the fiery core of a star, they remain in a state of suspended potential, forever on the cusp of stellar achievement but never quite crossing the threshold. While they don't emit the light or heat of a true star, their composition and size often place them in a unique category that continues to intrigue astronomers. Failed stars are a reminder of the universe's dynamic dance, where even near misses in stellar formation can reveal profound insights into the processes that govern our cosmic surroundings. As we peer deeper into the cosmos, these celestial audition tapes of failed stars offer glimpses into the cosmic conditions that govern not just the birth of stars, but the extraordinary possibilities within our universe. Jupiter's formation is a tale that begins nearly 4.5 billion years ago, right at the dawn of our solar system. Picture a vast disk of gas and dust swirling around our newborn sun, a cosmic nursery where planets were just beginning to take shape. Amidst this dizzying dance of particles, Jupiter started its journey. It began as a solid core, accumulating material through a process known as accretion. Over time, this core gathered a thick shroud of hydrogen and helium, the building blocks of stars. However, unlike its fiery cousins, Jupiter was missing a key ingredient: mass. You see, a body aspiring to become a star must reach a critical mass threshold, around 75 times the mass of Jupiter, to achieve the extreme temperatures and pressures necessary for nuclear fusion. This fusion is the heart of a star, where hydrogen fuses into helium, releasing the energy that lights up the cosmos. While Jupiter is undeniably massive, it simply doesn't have enough heft to set off this stellar chain reaction. It's like gathering enough wood for a bonfire but lacking the spark to set it ablaze. Jupiter's tail, therefore, is one of immense potential, a celestial giant forever on the brink of becoming a star. The conditions weren't right for ignition, and instead of a second sun, we have the magnificent gas giant we know today. This fascinating history of formation underscores the delicate balance of cosmic forces that determine the fate of celestial bodies, leaving us with a planet that serves as both protector and enigma within our solar system. As we unravel these mysteries of formation, we gain a deeper appreciation for the intricate web of events that shape our universe. The debate over whether Jupiter is truly a failed star is one that echoes through the corridors of scientific discourse. On one side, proponents of this classification point to Jupiter's size and composition, which closely resemble those of stars. They argue that Jupiter has all the ingredients, like hydrogen and helium, necessary for star formation, making it a logical candidate for a failed star. The fact that it didn't ignite into a star is not viewed as a disqualification, but rather as a testament to the delicate balance required for stellar birth. Some scientists even suggest that if Jupiter had accumulated more mass during its formation, it could have easily crossed the threshold into stardom. This perspective sees Jupiter as an almost star, sitting at the crossroads between planets and stars. On the opposite camp, skeptics argue that labeling Jupiter as a failed star oversimplifies the complex processes that differentiate stars from planets. They emphasize that the gap between a giant planet like Jupiter and a star is vast, primarily due to the lack of sufficient mass in Jupiter to sustain nuclear fusion. This core condition is what makes a star shine, and without it, Jupiter is simply a massive gas giant. Critics of the failed star hypothesis also highlight the unique characteristics that set Jupiter apart as a planet, such as its dynamic weather systems and powerful magnetic field, which align more closely with planetary behavior than stellar. Ultimately, the debate is not just about definitions, but about how we understand the mechanisms of celestial formation and the diversity of objects within our universe. This ongoing dialogue reveals the intricate details of planetary science and encourages a deeper exploration of the cosmos, pushing us to continually question and refine our understanding of the universe. Comparison with brown dwarfs, we find ourselves exploring an intriguing category of celestial bodies that straddle the line between planets and stars. Brown dwarfs are often referred to as failed stars because, like Jupiter, they don't have enough mass to sustain nuclear fusion in their cores. They sit in a sweet spot of mass greater than that of giant planets like Jupiter, yet not quite enough to ignite and become a star. While Jupiter might tip the scales at over 300 times the mass of Earth, brown dwarfs typically range between 13 and 75 times the mass of Jupiter. This places them in a unique niche capable of fusing deuterium, a rare isotope of hydrogen, although not enough to sustain full hydrogen fusion like a true star. In terms of composition, both Jupiter and brown dwarfs share similarities as they primarily consist of hydrogen and helium. However, brown dwarfs might contain more metallic elements and can emit faint glows from the residual heat of their formation. This emission often creates a dim, reddish hue, unlike Jupiter, which reflects sunlight and displays vibrant atmospheric patterns. Their formation processes also diverge slightly. While Jupiter formed from the accretion of gas around a solid core, brown dwarfs likely formed from the direct collapse of a gas cloud, similar to stars, but without attaining the critical mass needed for fusion. In this cosmic context, Jupiter and brown dwarfs present an intriguing study in contrasts and connections, highlighting the diverse outcomes of planetary and stellar formation. Understanding these similarities and differences not only sheds light on the intricate processes shaping our universe, but also enriches our appreciation for the variety of celestial phenomena existing just beyond our night sky. The role of hydrogen and helium in the formation of stars cannot be overstated. These two elements are the universe's most abundant and are the fundamental building blocks for star creation. When we look at stars, they are essentially enormous, glowing balls of gas composed primarily of hydrogen and helium. These elements engage in a powerful, continuous process known as nuclear fusion, where hydrogen atoms are fused into helium under extreme pressure and temperature conditions, releasing a tremendous amount of energy. This energy is what gives stars their light and heat. Now, considering Jupiter, it shares a strikingly similar composition with stars, being predominantly made up of hydrogen and helium. It's almost like seeing a star in its embryonic state, having amassed a significant amount of these crucial gases. However, despite having the right ingredients, Jupiter lacks the necessary mass to achieve the core temperatures and pressures required to ignite nuclear fusion. It's akin to having all the right components for a spectacular firework display, but not having the spark to set them off. Yet, Jupiter's immense hydrogen and helium reserves do not go unnoticed. They play an essential role in its identity as a gas giant and contribute to its imposing presence in our solar system. This composition also makes Jupiter a subject of wonder and speculation, as it hints at what could have been under slightly different cosmic circumstances. Thus, while Jupiter's alignment with stellar requirements is undeniable, its journey stops just short of stardom, offering us a unique opportunity to study a planetary giant that embodies both the potential and limitations inherent in the cosmos. This reflection on Jupiter's nature invites us to ponder the intricate processes that differentiate a planet from a star and appreciate the delicate cosmic balances that orchestrate the symphony of our universe. Jupiter's gravitational influence exerts a formidable force in our solar system, shaping its very dynamics much like a star's gravitational dominance over its surrounding celestial bodies. Imagine Jupiter as a massive anchor, its immense gravitational pull acting like a cosmic magnet that attracts and influences anything that comes too close. This gravitational force is so powerful that it plays a crucial role in maintaining the stability of our solar system. For instance, Jupiter acts as a celestial shield, its gravity capturing or deflecting asteroids and comets that might otherwise pose a threat to Earth and other planets. It's a bit like a giant bouncer at the entrance of a club, keeping unwanted visitors at bay. Furthermore, Jupiter's gravitational interplay extends beyond being a protector. It significantly influences the orbits of other celestial bodies in the solar system. For instance, it is largely responsible for the asteroid belt's current location, preventing these rocky bodies from coalescing into another planet through its gravitational pull. This influence extends to Jupiter's own moons, locking them in stable orbits and creating fascinating phenomena such as orbital resonance, where moons like Europa, Ganymede, and Io engage in synchronized orbits due to Jupiter's gravitational tug. By drawing parallels with stars, we see that just as stars hold sway over their solar systems, Jupiter's gravitational might ensure that our cosmic neighborhood retains its delicate balance. Its presence is a testament to the dynamic forces at play in the universe and offers us a glimpse into how gravity, whether through stars or massive planets, orchestrates the celestial dance of orbits and motions. This reflection on Jupiter's gravitational role invites us to appreciate the intricate web of interactions that our solar system relies on to sustain its harmony. In exploring this gravitational influence, we gain insight into the monumental forces that govern not just our own neighborhood, but the very fabric of the universe. The reason Jupiter cannot initiate nuclear fusion like the stars lies primarily in its insufficient mass and core conditions. To ignite nuclear fusion, which is the process that fuels stars, a celestial body needs to reach a specific mass threshold. This mass ensures that the core can achieve the immense pressure and temperature necessary for hydrogen atoms to fuse into helium, releasing energy. This process is what gives stars their radiant glow and heat. Jupiter, massive as it is, falls significantly short of this threshold. It would need to be about 75 times its current mass to create the conditions conducive to fusion. Without this additional mass, the pressures and temperatures in Jupiter's core remain far below the levels needed to start nuclear fusion. It's like trying to light a match underwater. The conditions just aren't right for it to ignite. Furthermore, Jupiter's core, while speculated to be dense, doesn't experience the gravitational squeeze that stars do. This squeeze is crucial as it facilitates the extreme conditions required for fusion. As a result, Jupiter, with its relatively cool and low-pressure core, is forever bound to remain a stunning gas giant rather than transforming into a luminous star. This distinction highlights the delicate balance of cosmic factors that dictate a celestial body's fate, reminding us of the intricate choreography at play in the universe's dance of planets and stars. Imagining Jupiter as a star takes us into a realm of fascinating possibilities, altering the very fabric of our solar system. If Jupiter were to ignite and become a star, this transformation would have profound consequences on the planetary orbits. The solar system, as we know it, would undergo a dramatic change. Currently, each planet orbits our single sun in a harmonious balance. However, introducing a second star in the form of Jupiter would upset this equilibrium. The gravitational forces exerted by a newly ignited Jupiter star would pull at the neighboring planets, potentially shifting their orbits. It's possible that planets could move into more elongated paths, leading to fluctuations in temperature and climate. Such changes could mean that Earth, our home, might experience shifts in its climate patterns, affecting life in unpredictable ways. Moreover, the increased radiation and heat from a second star might render some regions unbearably hot while others might cool down, depending on their new positions and alignment with both stars. The presence of another star could lead to chaotic gravitational interactions, causing the orbits of smaller bodies like asteroids to become erratic, increasing the risk of collisions with planets. While the night sky would be illuminated with an additional celestial glow, the risks and challenges of living in a dual star system would be significant. The delicate balance that supports life on Earth might be disrupted, potentially making it challenging for ecosystems to adapt. As we imagine such a scenario, it underscores the intricate interplay of cosmic forces that sustain our solar system, highlighting the fragility and wonder of the universe we inhabit. Visualizing a binary star system with Jupiter and the Sun invites us to imagine a cosmic dance unlike any other in our solar system. Picture our skies graced not by one but two radiant stars, each providing its glow and warmth. The Sun, our familiar source of light, would share the stage with a newly ignited Jupiter, transformed into a star. This celestial duo would orbit a common center of mass, a complex gravitational ballet that dictates the movements of such systems. Known binary systems in our galaxy vary in appearance and behavior. Some feature stars of similar size, while others, called binary pairs, consist of one massive star and a smaller, fainter companion. In our solar system, Jupiter would be the latter, a smaller star compared to the Sun. The dynamics of this binary system would be influenced by their mass and distance from each other. As in known binary systems, the gravitational interaction between the Sun and a star Jupiter would be substantial, impacting the orbits of planets and other celestial bodies. This interaction is akin to the tug-of-war observed in other binary systems, where planets might orbit around both stars in complex patterns or be captured by one star's gravity. The sight of two suns in our sky would be awe-inspiring, casting double shadows and altering the familiar patterns of sunrise and sunset. The increased radiation from a star Jupiter, though lesser than the Sun's output, could affect the climate and habitability of planets in their vicinity. This imagined scenario draws parallels with binary systems where planets manage a delicate balance in orbit, adapting to the dual influences of their stellar parents. Such systems, while fascinating, are rare for supporting life, as the shifting gravitational forces present unique challenges. Considering this, we realize the delicate equilibrium within our current single-star solar system and the extraordinary nature of binary star systems scattered across the cosmos. The theoretical energy output of Jupiter, should it transform into a star, is a fascinating topic that challenges our understanding of cosmic energy dynamics. Using scientific models and simulations, we can estimate what type of energy Jupiter might emit as a star. Currently, because Jupiter is not massive enough to initiate nuclear fusion, it resembles a cosmic furnace without a flame. Yet, if it somehow gained enough mass to cross the threshold, the energy released would be a product of hydrogen fusion in its core. This process would generate energy at a rate significantly lower than our Sun's output. Jupiter's smaller mass as a star would mean its energy output might be just a fraction, perhaps comparable to that of a small red dwarf star. Despite this relatively modest production, the impact on nearby celestial bodies would be immense. This influx of additional energy and heat could alter the icy surfaces of its moons, potentially thawing subsurface oceans beneath Europa's icy crust. The intensified radiation could also transform their atmospheres, perhaps inducing chemical changes on moons like Io or Ganymede. Beyond its own moons, the newfound stellar energy might extend its influence to the outer reaches of the solar system, affecting the Kuiper belt or even exerting subtle gravitational influences that could alter the orbits of distant celestial bodies. This hypothetical burst of energy uncovers the profound ripple effects of a new star within our celestial vicinity, illustrating the interconnected web of forces that govern our cosmic neighborhood. These possibilities highlight the intricate balance of solar system dynamics and underscore the fragile equilibrium that sustains the worlds within it. If Jupiter were to ignite as a star, the transformation would bring profound changes to its moons, fundamentally altering their atmospheres and surfaces. Picture Europa, known for its ice-covered surface and hidden ocean beneath. With the newfound heat from a star Jupiter, the icy crust might begin to melt, exposing the ocean to space and possibly creating a dynamic environment where liquid water interacts with the solar energy. This could lead to fascinating questions about the potential for life in these newly accessible waters. Ganymede, the largest moon in the solar system, might experience shifts in its icy surface and the potential alteration of its magnetic field due to the increased heat and radiation. Io, with its active volcanoes, could see these fiery features intensified, as the extra energy might fuel even more volcanic activity, altering its landscape dramatically. Callisto, often seen as a battered ice ball, could also undergo changes, perhaps developing a thinner atmosphere as the ice sublimates, contributing to a newfound gaseous envelope. Additionally, the transformed radiation environment would significantly impact all moons' chemical compositions and atmospheres, potentially increasing the presence of more evolved molecules. This atmospheric evolution might also lead to shifts in color, texture, and geologic activity, painting entirely new vistas on these celestial neighbors. As we consider these possibilities, it becomes evident that a star Jupiter would not only reshape the moons physically but also energetically, opening a realm of scientific inquiry into how life and geological processes might adapt or arise under such radical changes. Through this lens, Jupiter's moons become a fascinating case study in the adaptability and resilience of celestial environments to extreme conditions, showcasing the dynamic and ever-evolving nature of our cosmic neighborhood. The habitability of the solar system would face profound challenges if Jupiter were to transform into a star. Imagine the delicate balance that currently supports life being disrupted by a second sun, fundamentally altering the environment of planets like Earth and Mars. Earth's climate, closely tied to its position relative to the Sun, could experience dramatic shifts. The gravitational pull of a new star Jupiter might alter Earth's orbit, potentially leading to changes in temperature patterns. An elongated or shifted orbit could result in harsher seasons or unexpected climate extremes, challenging ecosystems to adapt quickly to new conditions. Furthermore, the increased radiation from a second star might lead to heightened levels of ultraviolet radiation reaching Earth's surface, affording greater risk to living organisms and potentially impacting the ozone layer. Mars, often considered for its potential habitability, would also face significant transformations. The heat from a newly ignited Jupiter could cause drastic temperature changes on Mars, impacting its ice caps and weather systems. This might lead to more volatile weather, with the possibility of atmospheric changes that could either aid or hinder future colonization efforts. While the idea of a dual star system evokes imagery of exotic, lively worlds, the reality might present insurmountable challenges for sustaining life as we know it. Planets like Earth and Mars thrive in a unique balance, and the introduction of a second star could tip these scales dramatically, creating a cosmic environment with unforeseen consequences. Such a transformation would prompt a re-evaluation of the habitable zone in our solar system, as new radiation levels and gravitational forces redefine where life could potentially exist. This scenario underscores the fragility of conditions that sustain life, prompting us to contemplate the resilience and adaptability needed to survive in such shifting cosmic circumstances. Can Jupiter become a star? When we dive into current scientific theories and technologies, we find a consensus that the transformation of Jupiter into a star is highly improbable under natural circumstances. One of the primary reasons is Jupiter's insufficiency in mass. To ignite nuclear fusion, a process that powers stars, a celestial body requires a mass at least 75 times greater than Jupiter's current size. This colossal mass results in the necessary core pressure and temperature to trigger the fusion of hydrogen into helium. In scenarios where we imagine adding more material to Jupiter, achieving the mass needed for stardom would involve acquiring an enormous amount of additional material, far more than what exists in our solar system, making this transformation practically impossible without extraordinary hypothetical means. Moreover, current technology does not provide any naturally feasible method to increase Jupiter's mass to such levels. Advanced propulsion systems and space engineering theories have not considered nor realistically devised a means to artificially induce such a transformation. This sort of celestial modification would require breakthroughs far beyond our present scientific reach, involving technologies that could manipulate planetary masses on a vast scale, an endeavor that remains speculative and squarely within the realm of science fiction. Alongside these challenges, there are also significant concerns regarding the stability of the solar system. Any manipulation of Jupiter's characteristics could disrupt the gravitational harmony that maintains the orbits of planets and other celestial bodies, potentially causing chaos in the established cosmic order. Thus, while the concept of Jupiter becoming a star captures the imagination, The scientific analysis points to the current impossibility of such a transformation within the bounds of our current understanding and technological capabilities. This exploration not only highlights the cosmic constraints that govern planetary and stellar dynamics, but also inspires ongoing curiosity and innovation as we continue to expand our comprehension of the universe. Jupiter's magnetic field and radiation belts are among the most formidable features that hint at its potent nature, inviting comparisons to stars and fueling the debate over its classification as a failed star. Picture this: Jupiter's magnetosphere is the largest structure of its kind in the solar system, extending millions of miles into space and dwarfing even the Sun's influence. Its magnetic field is some 20 times stronger than Earth's and is generated by the same process that occurs in stars, a dynamo effect where the movement of conductive materials creates intense magnetic forces. This similarity further blurs the line between planet and star, suggesting a stellar-like force at play within Jupiter. In addition to its magnetic prowess, Jupiter is encircled by intense radiation belts, similar to the Van Allen belts around Earth, but far more powerful. These belts are teeming with high-energy particles and present a radiation environment that could potentially rival that found around certain types of stars. The presence of such robust radiation belts indicates not just a magnetic strength, but also a star-like ability to trap and accelerate charged particles. This feature often leads scientists to ponder Jupiter's role as a cosmic powerhouse in the solar system, reinforcing the idea of it being a sort of cosmic anomaly, boasting characteristics that align it closely with the phenomena we associate with stars. In this context, Jupiter's magnetic field and radiation belts serve as compelling evidence in discussions concerning its potential classification as a failed star, highlighting its unique position at the borderline between a planet and a stellar body. This aspect of Jupiter not only fascinates scientists, but also challenges our conventional understanding of the boundaries that define planets and stars in the expansive tapestry of the cosmos. Exploring exoplanets and failed stars beyond our solar system offers incredible insights that enhance our understanding of Jupiter's position in the cosmic order. Imagine a universe teeming with diverse celestial bodies, some of which bear a striking resemblance to Jupiter's unique characteristics. Among these are the brown dwarfs, often considered failed stars, which share many traits with our gas giant. By comparing them with Jupiter, we gain a deeper appreciation for what distinguishes planets from stars. Brown dwarfs, like Jupiter, are not massive enough to sustain nuclear fusion in their cores, placing them in a fascinating gray area of stellar evolution. They sit squarely between the largest gas giants and the smallest stars, often categorized by their ability to fuse deuterium, a heavy isotope of hydrogen, unlike Jupiter. Additionally, with advancements in space exploration and technology, we've discovered numerous exoplanets around other stars that expand our context. Some of these exoplanets exhibit characteristics reminiscent of Jupiter, such as their vast size and gaseous composition, yet orbit different stars, revealing the sheer variety of planetary systems in the galaxy. For instance, the exoplanet HIP 34858b, located over 200 light-years away, is a gas giant with similarities to Jupiter, yet it resides in a distant system, providing a point of comparison to evaluate Jupiter's role within our own solar neighborhood. Observing these distant planets and failed stars informs our understanding of the processes that lead to their formation, offering clues to the conditions that either enable or prevent their ignition as stars. These discoveries suggest that there is a continuum rather than a strict boundary between planets and stars, with Jupiter eerily straddling this line. Through these cosmic comparisons, we are reminded of the rich variety and complexity of the universe and how Jupiter fits into this intricate mosaic. By studying failed stars and exoplanets beyond our solar system, we enrich our understanding of celestial dynamics and learn more about the delicate factors that determine whether a celestial body becomes a star or a planet. Jupiter in mythology and culture holds a place of immense significance, reflecting its awe-inspiring presence in the night sky. Ancient civilizations often associated Jupiter with their chief deities, attributing to it the traits of power and supremacy. For the Romans, Jupiter was the king of the gods, a symbolic ruler whose mighty presence was thought to control the skies and influence the fates of men. Similarly, in Greek mythology, the god Zeus overshadowed the heavens with thunderbolts and divine authority, mirroring the planet's grandeur and dominance. These mythological stories highlight how humans have long been captivated by Jupiter's majestic allure, crafting narratives that celebrate its celestial prominence. The Mesopotamians referred to it as Marduk, the supreme god responsible for creation and justice, while the Babylonians saw it as representative of their god Bel, emphasizing its sacred stature in their cosmology. Fast forward to modern times, and we see how these ancient myths intriguingly align with contemporary scientific discourse. The debate over Jupiter's potential status as a failed star echoes the godlike myths of old, suggesting a latent power within that universe watchers have marveled at for millennia. The planet's massive gravitational influence and swirling cloud bands still command our attention, leading to discussions about its role in the solar system and broader cosmic order. Mythology and science converge as both realms seek to unravel the mysteries of this giant, exploring its potential star-like qualities and what they reveal about our universe. This connection between ancient tales and modern astronomical inquiry offers a rich tapestry of understanding, one where cultural narratives and scientific exploration blend to enhance our appreciation of Jupiter's enduring legacy. As we explore these mythological ties, we see how they enrich our scientific curiosity, inviting us to reflect on the timeless wonder that Jupiter inspires both in our imaginations and in our quest for knowledge. The future of Jupiter, a celestial giant that has captivated humanity for centuries, holds intriguing predictions and possibilities as we continue to advance in astronomical research. Based on current scientific insights, Jupiter promises to maintain its pivotal role in the solar system's evolution, serving as both a stabilizer and protector. One of the most fascinating predictions involves Jupiter's continued gravitational influence, which acts as a cosmic guardian by shielding inner planets from potential asteroid impact. This protective role is expected to persist, maintaining a relatively safer path for Earth and its neighboring planets. Moreover, in the realm of space exploration, future missions are poised to delve deeper into Jupiter's atmosphere and its enigmatic moons, such as Europa and Ganymede. These missions aim to uncover secrets about potential subsurface oceans, offering clues about the conditions conducive to life beyond Earth. As technology advances, new methods of remote sensing and analysis could reveal unprecedented details about these moons' potential habitability. Scientists also predict that Jupiter's atmospheric dynamics, with its iconic storms like the Great Red Spot, will continue to provide insights into the complexities of gas giant planets. Studying Jupiter's perpetual storms assists researchers in understanding climatic patterns, not only within our solar system, but also in the wider cosmos, contributing to our knowledge of exoplanetary atmospheres. Additionally, Jupiter's magnetic field, a subject of immense scientific intrigue, is expected to remain a focal point of study as it presents parallels to stellar processes that inform our understanding of magnetic fields in broader astrophysical context. As we project further into the future, the possibility of harnessing Jupiter's immense resources, such as its hydrogen reserves, is contemplated within discussions of advanced space technology and energy. While these concepts remain largely theoretical, they illustrate the potential breadth of human ingenuity in leveraging extraterrestrial resources for sustainable energy solutions. In sum, Jupiter's future in the cosmic theater is cemented by its enduring influence and the vital role it plays in both protecting our planet and expanding the horizons of human discovery. Through continued exploration and scientific endeavor, Jupiter will undoubtedly remain a cornerstone in unraveling the mysteries of our universe, serving as a bridge between our current understanding and the uncharted territories of cosmic phenomena. Technological advances in observing Jupiter have taken us on an incredible journey from ancient stargazers to modern explorers, dramatically enhancing our understanding of this enigmatic giant and its potential as a failed star. Imagine looking up at the night sky through innovative eyes as astronomers have transitioned from simple telescopes to highly sophisticated instruments capable of revealing the intricate details of Jupiter's swirling clouds and magnetic fields. The advent of powerful ground-based telescopes like the Keck Observatory and space telescopes such as the Hubble Space Telescope have allowed astronomers to peer into the heart of Jupiter's storms, unlocking secrets within its turbulent atmosphere. These technologies have provided detailed images and data about the Great Red Spot, helping scientists to study its persistence and changes over time. Complementing these advancements, space missions have played a groundbreaking role in our journey to understand Jupiter. Missions like NASA Galileo, launched in the 1990s, provided pivotal data while orbiting Jupiter and even sent a probe into its atmosphere, revealing valuable information about its composition and weather systems. More recently, the Juno spacecraft has been orbiting Jupiter since 2011, offering unprecedented insights into its interior structure, magnetic field, and polar regions. Juno's instruments probe beneath the planet's cloudy veil, assessing its gravitational and magnetic fields, which enrich our comprehension of its formation and potential as a failed star. These technological endeavors underscore a significant leap in our observational capabilities, allowing scientists to explore hypotheses about Jupiter's star-like qualities. As we stand on the shoulders of these achievements, the continued development of more advanced space missions and observatories promises to shed further light on Jupiter's mysteries, inviting us to contemplate its role in our cosmic narrative with ever greater clarity. Continued exploration of Jupiter through various space missions has significantly contributed to our understanding and the ongoing debate about its nature. In the past, NASA pioneer missions in the early 1970s marked humanity's first close encounter with Jupiter. These spacecraft were the trailblazers, sending back data that laid the groundwork for future endeavors. They offered initial measurements of Jupiter's magnetic field and radiation belts, sparking interest in its potential as a failed star. Following this, the Voyager missions in 1979 explored Jupiter's complex atmosphere and discovered its faint ring system, broadening our understanding of this gas giant's dynamic features. Moving into the present, the Juno mission has been a cornerstone in unlocking Jupiter's secrets since its arrival in 2016. With its suite of sophisticated instruments, Juno dives deep into the planet's atmosphere, analyzing its magnetic field and assessing the water content in its clouds. These findings are crucial for assessing Jupiter's formation, providing insights into whether it harbors characteristics akin to a failed star. Juno's high-resolution images of Jupiter's poles have revealed cyclones unlike anything seen elsewhere, deepening our intrigue about its internal processes. As we look to the future, plans for upcoming missions suggest an ongoing commitment to exploring Jupiter's mysteries. The European Space Agency's Jupiter Icy Moons Explorer, scheduled for launch in the 2020s, aims to study the planet's large moons like Ganymede and Europa, which may harbor oceans beneath their icy surfaces. This mission hopes to uncover more about these moons' potential habitability, indirectly shining light on Jupiter's gravitational and dynamic influence. Additionally, NASA's upcoming Europa Clipper mission targets Europa's subsurface ocean with the potential to reveal conditions that might support life. These future missions promise to further our understanding of how Jupiter operates within the solar system and its potential role as a failed star. As exploration continues, each mission builds on the last, weaving a complex narrative that challenges and enhances our comprehension of this giant. Through these space endeavors, we remain committed to unraveling Jupiter's mysteries, showing that our curiosity knows no bounds as we strive to unlock the secrets of our cosmic neighborhood. Public fascination with Jupiter and the question of its status as a failed star captivates the imagination for several reasons. First, Jupiter's enormous size and unique characteristics make it a natural spectacle in the night sky, drawing interest and curiosity from people worldwide. The idea of a planet almost becoming a star but falling just short is an enthralling concept, akin to an astronomical what-if story that inspires wonder and speculation. It's a narrative that invites us to reconsider our understanding of the cosmos and the delicate balance required for celestial bodies to ignite as stars. This contemplation of Jupiter's potential stardom resonates deeply with our innate desire to explore the unknown and comprehend our place in the universe. Additionally, the public intrigue surrounding Jupiter is fueled by its prominent role in our solar system's dynamics, where its gravity shapes planetary orbits and acts as a cosmic shield. The notion that such a familiar giant could have transformed into a star offers a glimpse into alternate worlds and cosmic possibilities. This speculation bridges the gap between scientific inquiry and popular culture, inviting everyone to engage with the mysteries of space. The implications for science communication are profound. By tapping into the public's fascination with Jupiter, scientists and educators can foster increased interest in astronomy and the exploration of our solar system. Jupiter's story serves as a gateway to communicate complex scientific concepts in an accessible way, using its allure to promote learning and discovery. As a figure of both scientific intrigue and cultural significance, Jupiter becomes a powerful tool in inspiring the next generation of explorers and igniting a passion for understanding the universe. This engagement not only emphasizes the importance of science literacy, but also highlights the role of storytelling in bridging the divide between scientific knowledge and public understanding, ensuring that the wonders of space continue to captivate and educate people everywhere. In summary, the intriguing question of whether Jupiter stands as a failed star has taken us on an enlightening journey through the depths of our solar system and beyond. We've unraveled the majestic planet's remarkable features, its role in cosmic mechanics, and its tantalizing potential as a near-stellar body. Through examining its composition, gravitational influence, and comparisons with brown dwarfs and stars, we've gained insights that challenge our conventional understanding of planetary and stellar boundaries. The ongoing scientific discourse has illuminated the delicate orchestration of conditions required for star formation and the exquisite balance that defines our cosmic neighborhood. As we ponder the possibility of Jupiter's transformation into a star, we're reminded of the profound ripple effect such an event could have on planetary orbits and the habitability of worlds. This exciting narrative beckons us to continue exploring the universe's mysteries, enhancing our grasp of the celestial dance that unites planets and stars. We invite you to reflect on how this knowledge shapes our perception of the cosmos and the intricacies within it. If this journey through the wonders of our cosmic environment has sparked your curiosity, consider sharing your thoughts in the comments below. We would love to hear your perspectives on this celestial puzzle. Don't forget to subscribe to our channel for more exciting explorations of space, technology, and the fascinating possibilities they present for our future. Thank you for joining us on this cosmic adventure.